So Riccardo Orlando is going to present us a quantitative model for gender gap in the assessment at 8th grade.
You
Okay.
should be able to see my presentation now.
1 second. Online, you should already see the presentation, not in the room, so please wait for us. It's running faster online than it. Okay, here we are.
Okay.
Here we are.
So I am presenting a quantitative model for gender gap in grade 8 standardized mathematics tests in Italian schools. The gender gap problem is very well known, very well studied. We have particular interest here in Italy in the gender gap in mathematics. These are international results. You can see that while we score exactly the same average across all students, our gender gap is significantly greater than the international average. And just to reference INVALSI data, which I used for this study, this is the score distribution for a given year, and they all look like this. But if we split the distribution between genders, these are the results, and you can clearly see that while the shape is the same, the median is a few points higher for male students, which are in orange in this graph, while female students seem to lag behind. So browsing the literature, I found mainly two kinds of analysis. There's item level analysis, where a single item or very few items are considered and analyzed, discussed based on the didactic contract. This is very interesting, but of course it can only be done with very few items at a time. On the other hand, there's large-scale statistical analysis, which of course is very comprehensive, but it may be hard to gain insight and to connect the results gained from statistical analysis to actual properties of the items, the way they're constructed, the way students actually interact with the items. So the data used is grade 8 math tests from INVALSI. And I considered 8 years worth of tests from 2009 to 2017. The total, I had 342 total items, which were split equally into a construction set and a validation set, which we will see later why that was necessary. Why grade 8? Well, I need items from a single grade, and it is known that the gender gap grows with age. So that's an incentive to choose as late a grade as possible. However, after grade 8, in the Italian curriculum, students choose high school, and high school choice is heavily correlated by gender. So taking different curriculums makes the analysis much more difficult. So this is the highest grade in the Italian common curriculum. I begin by by quantifying discrimination with differential item functioning, which is very well known, very used in the literature. The short idea is that the student population is split in slices according to their total test score. And I compute a metric E where I divide the correct male answers times the wrong female answers, normalized over the total population. I divide by the opposite term, where the wrong male answers are multiplied with the correct female answers. And since the scale, the value produced by this measure is a multiplicative one, where a value of 1 means no discrimination, I pass the value through a logarithm, which is very popular in the literature. Unfortunately, every single paper I found used a different base for the logarithm and a different coefficient in front of the logarithm. So I did the same. I chose an arbitrary number, but my number is nicer. And the negative sign is there so that positive numbers correlate with items that favor female students, while negative numbers correspond to items that favor male students. So in the whole presentation, in general, positive values means that the item is better for girls, while negative values mean that the item is better for boys. And this is the distribution. These are 4 of the 8 years considered. We can see the way the item discrimination is distributed. And while the average discrimination is pretty close to 0, we can see that distributions have interesting tails. And it's especially interesting that there are a few items that heavily favor male students. You can see in the 2012-2013 year and in the 2015-2016 year. So, okay. Our model assumptions is that there are certain properties of items that cause their discrimination. And while it is known in the literature that a big part of the discrimination of the differences score is accounted for by social and sociological differences, there's still a slice that is not explained by social differences. And so we look for item level properties that may explain this difference. So I classify items. Items belong to categories, and each category has a discrimination value. And of course, the discrimination of an item, our model assumes, is the sum of the discriminations of the categories to which it belongs. So of course, calling D the vector of item discriminations, and classification matrix M, which is a binary matrix in which in position ij, I find a 1 if item I belongs to category J, otherwise I find a 0. And having the vector C of categories discrimination, then of course, this matrix multiplication should hold, by which I mean that multiplying the classification matrix with the categories discrimination should yield the item discrimination. Of course, it is the item discrimination which is known by the data. And so we estimate, we compute through a least square method, the categories discrimination. So the categories are chosen with a few constraints in mind. They're constructed only looking at items from the construction set, because of course, since I am the one constructing the categories and also classifying the items, I did not want to potentially bias my result by constructing the categories and then evaluating the same items I used to construct the categories. So I use the construction set to develop the categories, and they consider math skills required to complete correctly the item, language skills that the item demands, the way the item interacts according to the theory of the didactic contract, and finally, item presentation, the way the item is presented. Is it word? Does it have pictures? Does it contain a table? Things like that. This process yielded 16 total categories. For example, one category is standard arithmetic. An item belongs to this category if it is an arithmetic task that can be completed using only standard procedures, meaning only algorithms and strategies that are explicitly taught in the text and by the teachers in grade 8. Another category is redundant information. This category captures items that contain redundant or superfluous information, and we will see an example item in this category later. Another category is implicit assumption. This item contains an implicit assumptions or requires data which is not explicitly mentioned in the text. And finally, one category is numeric answer, which is items that have a single number as an answer with a unit of measure, or a small set of numbers as answer. The results on the validation set, while the model was run on the construction set, the results are not as interesting. We have a relative residue of 0.88, which is pretty high, but that was to be expected. There are 3 categories with insufficient items. That's one of the risks of constructing categories on a set of tests and then evaluating other items. There are 8 categories with very low discrimination, and there are 5 categories with, I say, interesting results. They have relatively high discrimination in either direction, both positive and negative. And we will see we will see, they are coherent with the didactic contract, by which I mean that, for example, one category with an interesting high discrimination value is the explain your reasoning category, with a discrimination of 6.9, which is positive, so it favors female students. And it is known in the didactic contract the effect of the need for formal justification, and we know that this impacts differently female and male students. Another category with a high discrimination value is asymmetric distractors, with a discrimination of negative 9.3. This is negative, so it favors male students. This is because it corresponds with the tendency to discard extreme options. And the category, which I named extrapolate, with a discrimination of negative 6.3. And we see that this corresponds with the tendency to only use values that are explicitly mentioned in the item's text. An example item of a category explain your reasoning, which had a discrimination of 6.9, is this one. And I'll try to translate it for the English-speaking audience. The item's text says, a medicine is sold in boxes of 28 tablets, which can be split as in the picture. Each tablet is 20 milligrams. Piero's grandmother must take every day for a month 30 milligrams of this medicine. For how many days can Piero's grandmother take this daily dose of the medicine using a single box? Write how you found the answer and then write the answer. So the interesting part, the part that according to the results induces the discrimination, is exactly this write how you found your answer, or in general, the need to explain the reasoning. It is known in the literature, and it is confirmed by this result, that female students fare better in these kind of tasks where they have to employ their language skills, and they can follow the way the exercises were structured and practiced in the classroom. Another example for the category asymmetric distractors, with a discrimination, with a category discrimination of negative 9.3, is the following. This table reports data on citizenship of students enrolled in a school. And the table reads type of school, total students, Italian students, foreign students, and percentage of foreign students. And then the pupil taking the test is asked to compute the percentage of foreign students of the whole school. And this item is interesting because the correct answer, which is item D, is the lowest of the 4 presented options. And so if the students who are uncertain of the correct answer tend to discard extreme options because they have learned that it is often the case that correct answer lies in the middle of the range of the proposed possible answers, then they are more likely to discard option D, or to doubt themselves if the computation they perform yields option D. And we see that this effect is different for female and for male students. In fact, this effect is disfavors female students because the category discrimination is negative. Another example item, which belongs to the category extrapolate, and this also has a negative discrimination, and we will see why female students struggle with this kind of item. The text reads, Giovanni pours 100 milliliters of water at a time in the flask in figure up to 800 milliliters. Every time he marks with a mark on the flask the level that the water reached. How is the distance between marks marked by Giovanni? And this item is interesting because it is not possible to answer this item with a computation. And it is known in the literature and by the didactic contract, the effect as the need for formal justification, which shows itself as the need to justify the answer through some computation. And it is in fact known that if you, for example, if this type of item was an open answer item, if it did not have multiple choices, a significant amount of students would perform some calculation, for example, multiplying 800 by 100 or dividing 800 by 100, because they have learned that they have to justify their answers in a math test with some kind of computation, even if it is the case in the item that there is no need for any computation. Instead, they have to intuit, to extrapolate the answer based on other properties, not non-numeric properties of the text. So these are my results. There is a lot of room for further development. For example, new categories can be developed, and they could be developed based on those that worked here, or based on the didactic contract, since it appears that categories, functional categories, match the effects that are already known in the literature. Of course, this type of analysis could be applied to different grades. Lower grades would probably require different categories as well. And there's the problem in applying this to higher grades on how to correct, how to compensate for the differences in curriculum, which are highly correlated with gender. And well, speaking with INVALSI people earlier, I realized there's no reason to suspect that this couldn't be applied to also to language tests, to the Italian tests, INVALSI tests. Thank you for your attention.
Thank you very much, Riccardo, for your very interesting presentation, something brand new to me at least. Thank you very much. Questions, please. Giovanni, the one who was filling the bottle. Please, Giovanni.
So thank you very much. I found your presentation very interesting. Two things immediately. I had two flashes about the implications of what you just made. So the first one is that computing and studying cross-national differences in the gender gap is dangerous if you don't know how the tests were built. So you should rely only on standardized measures built in the same way, like TIMSS, PISA, or PIRLS, and not tests performed only in one country, like the national INVALSI of Spain against the one of Italy, for instance. And the second thing that I was thinking is, it seems that the math gender gap in the measurement is partly dependent on the type of tests that we think it is better to capture mathematical competences. But as you showed in the various your early graph, this is different year to year. So the question is, does the gender math gap exist, or it is a feature of the testing? It's a very clear-cut question, but I think you know what I mean, or I hope.
Well, in regards to your first point, I wasn't very clear in my presentation, I realize now, and I think I'll share my screen again to show the at-home audience. If I go back to the first graph I showed, this is not from national tests. This is, and I just realized I cut the legend. These are international tests, so every country took the same test, or a representative sample of students from each country took the same test. And this is why we can claim that there are differences, and that the gender gap in Italy is comparatively worse than in other countries. And these are not the whole results, they wouldn't fit in the slide. But okay, so on to your other point, I'm not sure if you're asking whether the gender gap grows with the student's age, or whether the gender gap changes in time, as in, so grade 8 students from 10 years ago had a different gap from grade 8 students today. Is that what?
To what extent it is a feature of the way in which we build the text, the test, and to what way it is something, the gender gap that, put it very roughly, actually exists. Because if we had tests made only by items in the first category that you illustrated, we would have a gender gap favoring girls. That was my argument. So to what extent it is, so math competences, we use this score, we take it for granted that is accurately measured, but there are quite some issues on its definition, apparently.
Okay, so on the one hand, pretty much every kind of standardized test, be it national, international, reveals a gender gap, a performance gap between males and females. And the gap is pretty consistent between different tests from different organizations. And it is possible to glean some insights also using university entrance tests and things like that, although those students are self-selected, so it's much muddier. And so on the one hand, the gender gap does exist, it's pretty clear. On the other hand, yes, the kinds of item and also the way the items are presented matters a lot, which is exactly the kind of thing I'm trying to investigate with this study. And it is, for example, known that, just to take a very simple example, I think grade 5 students asked to compute 2 plus 0.5, give a certain answer with some probabilities, whereas if they're asked to add 0.5 plus 2, the distribution of the answers changes drastically. So there's very interesting effects that are hard to analyze. So yeah, the way the item is presented matters a lot.
Other questions in the room or at home, please? If not, I have one. I really appreciated what you presented, and I was somehow wondering the same question that Giovanni asked, that is, to what extent the way we design the tests generate results. And what you said was really clear and saying it's a matter of sometimes rewarding the test in order to avoid discrimination in the items. Coming back to your analysis, it seems that among the several item characteristics that you used, only few matters, right? And the few that you showed us are more linked to not a formal element of the test, but more to the, I would say, to some specific sub-skills, to some specific processes.
Okay.
So my suggestion and my question to you is maybe more sharp in dividing the formal item characteristics where it is proper taking seriously the risk of discrimination and being more careful in avoiding to generate through discrimination bias in measures, from the items where instead we are simply processing different sub-skills. I don't know if it is clear, but I think that there are two levels that somehow in your presentation are not fully separated, and maybe fully separating them would be more useful for people working with tests.
Okay, so
you get the point?
The problem with this idea, if I understood you correctly, is that in a sense, if items are testing different subskills and male and female performance on those subskills is different, then that also reveals a kind of discrimination. I mean, we're just moving the problem from the whole of math performance to the performance in this specific subskill. And while I suspect it possibly could be done, the problem and the reason why many of my items were inconclusive is that this kind of analysis requires a lot of items. Like my data set is not the 5 million student answers, it's the 340 items, which are not very many even after 10 years of tests. So
your point.
I mean, I believe it were 3 or 4 categories I had to throw away because there were only 2 or 3 items in that category in the validation set. So they did show very high discrimination, but I couldn't show them because, I mean, if a single item has very high discrimination and there's one category to which it belongs, then it's not very indicative of the strength of that, the result. So in a sense, we are limited by the amount of items which allowed us to pick to specific subskills.
That's clear. Thank you again. Thank you very much. It was very stimulating. Thank you. So please.